Okay. Good morning to everyone. Thank you for coming for the second session of this morning session. We start on the symposium of today's symposium on mass spectrometry. And the first presentation, the role of mass spectrometry in the measurement of vitamins and their metabolites, focus on vitamin D metabolites, will be presented by Dr. Markus Herrmann. Professor Herrmann is the professor of laboratory medicine at the University of Graz, Australia, and the director of Clinical Institute on Laboratory Medicine of the University Hospital of Graz. After a big history of stages around the world, he will come here to present us the role of mass spectrometry on vitamins. Professor Herrmann, you have the podium.
Well, good morning, everyone. First of all, Australia is just one L difference, but it's a different part of the world. So thank you very much for the organizers for the very kind invitation to attend the 22nd National Greek Congress of Clinical Chemistry here in the historic city of Athens. It's a true pleasure for me to speak at this prestigious event, and I have decided to use the opportunity to introduce you into a novel metabolic approach to diagnose vitamin D deficiency. Now, here are my disclosures. Actually, none of them relates to the content of today's lecture. And this is the outline of my presentation. I will start with a brief excursion into the biochemistry and physiology of vitamin D, followed by some epidemiologic data regarding the prevalence of vitamin D deficiency in Central Europe. Then I will recapitulate with you the current approach to diagnose vitamin D deficiency and explain you the limitations. And then in the second part, I will introduce you to our novel metabolic approach, and I'll highlight the advantages of this approach. But let me start with some words about the biochemistry and physiology of vitamin D. Now, most of the body's vitamin D is skin-derived vitamin D3, whereas food-derived vitamin D2 accounts for a maximum of 10% of the total vitamin D. Vitamin D supplements can contain either D2 or D3, depending on where you purchase your supplements. However, both forms of vitamin D are inactive and require 2 hydroxylation steps in order to obtain biological activity. Now, the first hydroxylation in position 25 occurs in the liver, and the resulting 25-hydroxyvitamin D is the most abundant vitamin D metabolite in blood, but it is still inactive. The active compound, 1,25-dihydroxyvitamin D, is mainly synthesized in the kidneys on demand. And as it is synthesized on demand, this metabolite does not represent an individual's vitamin D status. This is important to keep in mind. Now, assessment of vitamin D status is one of the most frequent requests in medical laboratories worldwide. And current guidelines unanimously recommend the measurement of 25-hydroxyvitamin D for this purpose. Although interpretation of the results differs between countries and regions, as you can see in this table here, there seems to be a consensus that concentrations below 50 nanomoles per liter indicate vitamin D deficiency. So with this very basic knowledge, we are ready to look at the first clinical case. A 15-month-old boy who recently moved with his family from London to Sydney. His laboratory results show a markedly raised alkaline phosphatase activity in conjunction with low calcium and phosphate concentrations. Now, this pattern is highly suspicious of secondary hyperparathyroidism due to vitamin D deficiency. In fact, subsequent measurements confirmed a significantly increased PTH and an undetectable vitamin D. Now, severe vitamin D deficiency, such as in this case, leads to a disease known as rickets, where the growth and development of long bones is impeded. The bones of these patients are insufficiently mineralized, rendering them soft, so they buckle under mechanical load. Now, rickets were discovered more than 100 years ago by Werner McCullum and John Howland, and despite the fact that we have a cheap and sufficient tool to prevent and treat the disease, it is still rather common in industrialized countries. And this landmark study from my good colleague and friend Etienne Cavalier from the University of Liège in 1,200 Belgian infants, children, and adolescents demonstrated a prevalence of over 50% of vitamin D deficiency in this population, and severe vitamin D deficiency was seen in 15%. So these are really alarming figures. In fact, the prevalence of vitamin D deficiency is even higher in children than in the general Central European population, where approximately 40% and a little less have vitamin D deficiency. As I've just illustrated, the diagnosis of vitamin D deficiency is currently based on universal 25-hydroxyvitamin D cutoffs that apply to all patients. But what is the scientific evidence that supports these cutoffs? Now, the currently used 25-hydroxyvitamin D cutoffs have been derived from fracture studies, such as this one from Professor Heike Bischoff-Ferrari, showing a decreasing fracture risk with increasing concentrations of 25-hydroxyvitamin D. However, I want you to note that confidence intervals are wide. And if you look at the entire body of literature, you will soon note that the many existing studies are highly inconsistent. Therefore, you need meta-analysis, such as this one from Wang and colleagues, to demonstrate small effects that are not always significant. In addition to fracture studies, it has also been shown that below the currently recommended cutoffs for 25-hydroxyvitamin D, the prevalence of osteomalacia and rickets increases. Primel and colleagues analyzed bone calcification histomorphometrically in iliac crest biopsies from 675 donors. More than 2% of unmineralized osteoid, shown here in red and represented by the red horizontal line here, indicates osteomalacia, and this is a conservative cutoff. So above 75 nanomoles per liter of 25-hydroxyvitamin D, which is the preferred cutoff of the endocrinologists, not a single subject in this study presented with osteomalacia. Below this cutoff, the number of individuals with osteomalacia increases with decreasing concentrations of 25-hydroxyvitamin D. However, the vast majority of individuals with low 25-hydroxyvitamin D concentrations has no or has adequately calcified bone tissue, so no evidence of osteomalacia. So in summary, and these were just a very few examples of the existing evidence, in summary, the evidence that supports the currently used cutoffs for 25-hydroxyvitamin D is not as strong and convincing as many of you would believe. And in fact, many patients are diagnosed vitamin D deficient without having any evidence of adverse alterations of their bone metabolism or an increased fracture risk. This brings me to a second case that I would like to show you. A 65-year-old female who presented with fatigue, a history of hypertension, and multiple myeloma. The laboratory results show a pronounced hypercalcemia and a 25-hydroxyvitamin D in the toxic range. Parathyroid hormone was at the lower limit of reference, excluding hyperparathyroidism as the underlying cause of her hypercalcemia. Now, hypervitaminosis D is another well-known cause of hypercalcemia. But in this case, the low 125 dihydroxyvitamin D was inconsistent with the very high 25 hydroxyvitamin D, which was measured by an automated immunoassay. Based on this knowledge, then the 25 hydroxyvitamin D was repeated, but this time with an LC-MS-MS method, and the result returned within the desirable range. So hypervitaminosis D was also excluded as the cause of hypercalcemia in this patient. Now, as I've just mentioned, and we have heard it repeatedly during this conference, 25 hydroxyvitamin D, as well as many other steroid compounds, can be measured either by immunoassay or by LC-MS-MS. Now, the automated immunoassays have a low cost, are widely available, are easy to perform, and allow high sample throughput. And that's why many laboratories use them. But they offer a highly variable analytical performance. They often cross-react with chemically related steroid species. There is a risk of incomplete protein separation, especially in specific patient populations, and they are often subject to matrix interferences. Now, LC-MS-MS offers high sensitivity and specificity, allows multiplexing, and or matrix interferences are rare, but you need expensive equipment, highly qualified staff, which increases your cost, and sample throughput is still limited. Now, in our patient, there was a very high paraprotein that probably cross-reacted with the anti-25 hydroxyvitamin D antibody of the immunoassay, resulting in a low amount of chemiluminescence. When you use a competitive immunoassay such as this one, then this translates into a falsely high analyte concentration. And I want you to remember that paraprotein can disturb many assays that we use in the medical laboratory by various mechanisms. So the mechanism of interference is not always the same. And one interference that I would like to mention particularly are heterophilic antibodies, because they are much more common than most of you believe. So probably 3 to 5% of the general population have heterophilic antibodies, and they can randomly interfere immunoassays of all kinds. In our patient, the hypercalcemia was due to her multiple myeloma and not to hypervitaminosis D, as might have been suggested by the initial set of results. LC-MS not only offers high sensitivity and specificity, but also permits the simultaneous measurement of multiple vitamin D metabolites. And this allows a functional assessment of vitamin D metabolism, and how this works I will show you in the remaining time of my presentation. And I would like to start the second part with another clinical case. A 51-year-old male of African descent with dark skin. He presented for a general health check-up to his GP, and previously he had a bone mineral density measurement done by DEXA, and the bone mineral density was perfectly normal. The laboratory results show normal calcium and parathyroid hormone concentrations despite a low 25 hydroxyvitamin D. Now, according to the current guidelines, this patient has vitamin D deficiency, and many colleagues probably would recommend supplementation. However, there's increasing evidence that the currently used universal cutoffs for 25 hydroxyvitamin D are not applicable in all patient groups, and that 25 hydroxyvitamin D is not necessarily the best indicator of vitamin D status. In this study, Berg and colleagues demonstrated on average a 40% lower 25 hydroxyvitamin D concentration in Black individuals despite comparable parathyroid hormone concentrations and comparable bone health. At this point, I would like to make a brief excursion into the catabolism of vitamin D. Excess amounts of vitamin D are eliminated by an additional hydroxylation in position 24, which occurs primarily in the kidneys, but also in several other organs and tissues, such as the liver. The 24 hydroxylated metabolites are further processed and ultimately eliminated from the body. Now, the current approach to assess vitamin D status in patients by evaluating their vitamin D stores through a measurement of the inactive precursor 25-hydroxyvitamin D is flawed by the fact that you are essentially measuring the amount of fuel in the tank of your car. And we all know, if you still have a traditional car and not an electric car, that a car can drive equally fast with a full, a half full, or a nearly empty tank. And it may not even drive at all if fuel is not properly injected into the engine. Therefore, measuring simultaneously the principal catabolite, 24,25-dihydroxyvitamin D, provides important metabolic information that is similar to the exhaust gas that comes out of your engine. And the two metabolites can be combined in the vitamin D metabolite ratio, which normally ranges between 4 and 12%. Now, this comparison of black and white individuals nicely illustrates the limitation of assessing vitamin D status by 25-hydroxyvitamin D only. At any given parathyroid hormone concentration, black individuals, on average, have a 40% lower 25-hydroxyvitamin D concentration without having any disadvantage in terms of bone health or fracture risk. Replacing the 25-hydroxyvitamin D on the y-axis by the vitamin D metabolite ratio completely eliminates the issue, and both ethnic groups have comparable values. So this suggests that the vitamin D metabolite ratio is better suited to assess vitamin D status in black individuals. In our patient, the vitamin D metabolite ratio was 7.6%, which is perfectly within the reference range, and therefore this man is unlikely to benefit from any kind of vitamin D supplementation, and I would not recommend it. Now, in our laboratory, as you can imagine, we have an LC-MS method established that simultaneously measures 24,25-dihydroxyvitamin D and 25-hydroxyvitamin D with good sensitivity, specificity, and imprecision. And what you can get out of such a method in your laboratory is nicely illustrated by the case of this professional tennis player. He visited our hospital because of persistent hypercalcemia, muscle cramps, and spasms, particularly during the outdoor season when he was out on a tennis court. He also took vitamin D supplements, and his vitamin D was in the high desirable range, so everything normal. But his 24,25-dihydroxyvitamin D was extremely low, and so was his vitamin D metabolite ratio. Now, this situation reminds me of something like an endogenous vitamin D intoxication, where the person cannot get rid of excess amounts of vitamin D. And this can occur when your 24-hydroxylase enzyme is defective, and in fact, subsequent molecular testing revealed a homozygous mutation in the ZIP24A1 gene in this patient. Now, admittedly, such enzyme defects are rare. However, this study by Cavalier and colleagues produced first evidence that supports the utility of vitamin D metabolite measurement also in the general population. In 1,200 Belgian infants, children, and adolescents, they showed that with decreasing 25-hydroxyvitamin D concentrations, the percentage of individuals with undetectable 24,25-dihydroxyvitamin D increases massively. And this suggests that many of these individuals here do not have 25-hydroxyvitamin D to spare for catabolism, because they need every molecule to maintain calcium and phosphate homeostasis. Next, we wanted to understand if vitamin D metabolite measurement is also useful in a mixed adult population. And for this purpose, we measured vitamin D metabolites, parathyroid hormone, and biochemical bone turnover markers in over 4,000 serum samples from 2 independent cohorts, DESIRE and LURIC. Now, DESIRE consists of 2,010 Austrian blood donors without specific disease, whereas the LURIC study includes patients with acute cardiac symptoms that subsequently underwent cardiac catheterization. And these patients were also followed up for 10 years. Now, we used the DESIRE cohort to explore vitamin D metabolite levels in a mixed adult population without specific diseases. So they all fulfilled the requirements to be a blood donor. So the median 25-hydroxyvitamin D concentration was 68 nanomoles per liter, which indicates a rather good supply of our local population with vitamin D. D2 accounted for only 2%, which is in line with what I've shown you at the beginning of my presentation, and the median vitamin D metabolite ratio was 7.3%, with an interquartile range from 6.1 to 8.8. The median 24-25 dihydroxyvitamin D concentration was almost 5 nanomoles per liter, and the interquartile range indicates that 25% of our participants had a concentration of less than 3.42 nanomoles per liter. Now, when we account for some measurement uncertainty and round this to the next full number, we get 3 nanomoles per liter. And then we postulated that subjects with less than 3 nanomoles per liter of 24-25 dihydroxyvitamin D probably have a vitamin D metabolism that is pushed to its limits. Now, applying this criterion to the DESIRE cohort, we noted that in both groups, with and without relevant concentrations of 24-25 dihydroxyvitamin D, there were numerous individuals with deficient and sufficient 25-hydroxyvitamin D concentrations, but their PTH and vitamin D metabolite ratio levels did not differ. They were comparable. So this raises the question, are these individuals here really vitamin D deficient or not? And I want to remind you that only a limited number of individuals with low 25-hydroxyvitamin D levels actually has evidence of osteomalacia and rickets. Similarly, in the group with very little 24-25 dihydroxyvitamin D, there was also a considerable number of individuals with deficient and sufficient 25-hydroxyvitamin D concentrations. And again, this raises the questions, are the deficient ones really deficient and the sufficient ones really sufficient? We don't know. Again, their PTH and vitamin D metabolite ratio levels were comparable. So we don't know. Then, by convention, we assumed that this group here, with less than 3 nanomoles per liter of 24-25 dihydroxyvitamin D and very little 25-hydroxyvitamin D of less than 25 nanomoles per liter, they must be vitamin D deficient, functionally vitamin D deficient, because they have the highest PTH and the lowest vitamin D metabolite ratio of all groups. And the vitamin D metabolite ratio of this group was 3.75. When you round this, you come to 4%, and then we postulated, if you fulfill both criteria, a 24-25 dihydroxyvitamin D of less than 3 and a vitamin D metabolite ratio of less than 4%, then you probably have functionally relevant vitamin D deficiency. Now, next we applied this criterion to both cohorts, DESIRE and LURIC. And this plot illustrates the lack of specificity of 25-hydroxyvitamin D to diagnose vitamin D deficiency. For example, in the group with functional vitamin D deficiency, here and here, there was a high number of individuals with sufficient 25-hydroxyvitamin D concentrations. Yeah? And vice versa, in the group with functional vitamin D deficiency, there was a considerable number of individuals with low 25-hydroxyvitamin D concentrations. So clearly, 25-hydroxyvitamin D is not a really good indicator of how well your vitamin D metabolism is running. So next we wanted to understand if our metabolic approach is of any clinical relevance. And for that purpose, we measured PTH and the biochemical bone turnover markers CTX1, P1NP, and osteocalcin in both cohorts. Now here we compared the traditional approach with our functional approach. And the first thing we noted is that with the traditional approach, many more individuals were identified as vitamin D deficient when compared to the functional approach. And vice versa, with the functional approach, vitamin D deficiency was excluded in many more individuals than with the traditional approach. Furthermore, individuals with a deficient 25-hydroxyvitamin D concentrations below 50 nanomoles per liter have small, slightly, but significantly higher PTH and bone turnover marker concentrations than sufficient individuals. But the difference is so small that you might question the clinical relevance. With the functional approach, these differences are much more pronounced, and this indicates that individuals with functional vitamin D deficiency have accelerated bone turnover. And accelerated bone turnover is an established risk factor for osteoporosis and fractures. In contrast, vitamin D sufficient individuals had comparable PTH and bone turnover marker concentrations regardless of the approach used, which means we don't miss anything here. Even in the group with deficient 25-hydroxyvitamin D concentrations, but no evidence of functional vitamin D deficiency, PTH and bone turnover marker levels were almost identical. Now you can say, okay, that's all nice, this is a laboratory phenomenon. So therefore we wanted to ask if this has any relevance for the patient's outcome. And therefore we analyzed 10-year all-cause mortality in the LORIC cohort. Now, in individuals with no vitamin D deficiency, all-cause mortality was 18%, regardless of the approach used. All-cause mortality was highest in individuals with functional vitamin D deficiency, 48%. And in this group, all-cause mortality was significantly higher than in the group with only a deficient 25-hydroxyvitamin D concentration. So clearly, there is a clinical correlate of this metabolic approach. It seems to have relevant benefits. And with this, I would like to summarize. So the prevalence of vitamin D deficiency is high, and it seems to be highest in children and adolescents. This is quite alarming, up to 50%. The current approach to diagnose vitamin D deficiency is based on a measurement of serum 25-hydroxyvitamin D, and interpretation is on the basis of universal cutoffs, either 50 or 75 nanomoles per liter. But with a simultaneous measurement of 25-hydroxyvitamin D and 24,25-dihydroxyvitamin D, you can make a functional assessment of vitamin D metabolism, which seems to have an improved specificity. So you diagnose less people with vitamin D deficiency, and these are probably the ones that really do have a functionally relevant vitamin D deficiency. And therefore, this correlates better with clinical outcome, bone turnover, and all-cause mortality. And it seems to have particular advantages in specific patient groups, such as Black patients, pregnant women, probably dialysis patients. Before I close, I would like to thank my colleagues from the University of Graz, the University of Heidelberg, and the University of Liège in Belgium, who contributed to all this work. And with this, I would like to leave you with some images from the beautiful city of Graz, and a very famous quote from Graz's most famous citizen, ex-citizens, Arnold Schwarzenegger, who once said, "Hasta la vista." Thank you for your attention, and I'm happy to take questions.
Thank you, Herman, for your presentation. It was very interesting, and I don't know how we have to convince our administrators that we have both measurements in order to well define if there is deficiency or not of vitamin D. And I wasn't aware about this huge difference between vitamin D levels between African origin and Caucasians, to use the right terminology. But there are questions.
Okay, thank you, Marcus. This is excellent, and actually it fits in the puzzle of vitamin D testing and inconsistencies. So what's your opinion about vitamin D binding protein? How can it fit, and maybe it's another parameter that can be included in the bioactive vitamin D equation?
Well, we have, if you look it up, we have written a review article about all these various parameters of vitamin D metabolism. So I personally do not think that free or bioavailable vitamin D will ever make it into the clinic for various reasons, because you need 3 different analyses with all the measurement uncertainty and the limitations associated to them. This is almost not standardizable. And one major reason is that vitamin D binding protein, you need to measure it by mass spec. Because if you use an immunoassay, there are different forms based due to polymorphisms, and in fact, these polymorphisms explain the lower levels of 25-hydroxyvitamin D in the black population, because they have a lower affinity for 25-hydroxyvitamin D, and therefore less vitamin D circulates. But this is irrelevant, because it's the free or the bioavailable fraction that is relevant for the metabolism, not so much how much you have in your tank. So it is relevant, but measuring it is difficult. You need mass spec if you want to get a proper result. And as far as I know, there has not been shown any clinical relevance or superiority in measuring it.
Thank you very much. So we pass to the second presentation. Thank you, Herman.
Okay. The title of the second presentation is Advances in the Metrological Aspect of Mass Spectrometry by Dr. Kakoulidis Ilias, who is head of the Chemical Metrology Service, General Chemical State Laboratory.
Well, good afternoon. Thank you very much for the invitation. I would like to thank particularly Dr. Haliassos and Dr. Makris for this connection that we're having the past 6 years. Unfortunately, the Chemical Metrology Department of the State Chemical Laboratory is not involved in clinical measurements, because there is no way that a clinical sample can reach our laboratories due to authorities and the Greek legislation. But we are trying to find a possible way of getting in some cooperation. So let's see that 25 years ago, when I joined the State Chemical Laboratories, mass spectrometers were not easy to find around. There were only 3 spectrometers. You can see them. They are still working. They are working in other applications that were supporting at the time, in easier, let's say, applications, because now we have much better instruments to work with, and hopefully we will get our hands into much more, let's say, unfortunately expensive, but more accurate instrumentation for the reasons that were needed in the laboratory. Typically now the State Chemical Laboratory is equipped with a high-resolution UPLC MS system, a UPLC QTOF MS system, triple quads, both in LC and GC, and hopefully next year is going to have a high-resolution Orbitrap system, second one, and 2D GC high-resolution MS. This is not all. We have many other versions of mass spectrometers in the State Laboratory that are used in various applications, other than, unfortunately, clinical measurements. But let's see first why we are here. We want to present what the metrology community is doing presently for the supporting traceability of chemical measurements and focus on clinical measurements in particular, and see how we're going to keep on doing this work, because one of the biggest requirements in measurement is the traceability of measurement to the SI, to the International System of Units. So to get to know each other, the Laboratory for Chemical Metrology, short HIM, it comes from the Greek acronym for Laboratory of Chemical Metrology. It is situated in Athens, actually a quarter of an hour from here on foot. And the National Measurement Institute is located in Thessaloniki. It has no capabilities on chemical measurement, so it designated this particular function to the State Chemical Laboratory in 2009. What we serve is and we function under is the mutual recognition arrangement that supports the equivalence of measurements throughout the world. You have to have a common reference in everything so that you can have measurements to be, let's say, have a clinical test in Athens, and if I get tested the next day in Australia, I get the same results. So you need a common reference. And also this system supports comparability both in time, because you need to see how your measurements are evolving. Who is doing all this work? This is under the authority of the Bureau International de Poids Mesures in France, under the Meter Convention, which was a result of the French Revolution, I have to remind you. And it's one of the oldest, let's say, worldwide treaties, back to the 1876. And in particular, for chemical and biological measurements, the Consultative Committee for the Amount of Substance is responsible for setting up the system in chemistry and biology. There are several working groups according to the basic measurements that are being, let's say, followed. Of relevance to us, and in Greece, we are active in this part, in inorganic analysis and organic analysis. We are doing very few things on isotope ratio mass spectrometry, and we are slowly getting into the protein analysis working group. The reason is because in all other measurements, except for clinical measurements, peptides and proteins are hardly measured. So how is this, let's say, system functions? All the metrology institutes participate in comparisons that are being performed under the auspices of the BIPM or the Regional Metrology Organization, Euramet for Europe, and they provide their measurements if they are successful, like you are in a proficiency testing, let's say, putting it simply. Then you can claim you have capabilities of measuring different things in several substrates, like metabolites in blood, which is the case in clinical measurements. And then there is a system that these are approved, and these capabilities are fed in the King Comparison database system, which is free for everybody in the internet. Everything that I will show you here, you can find it on the internet, is free for everybody to see. So the organic analysis working group, you can see since 1999, when it started its operation, has organized, I think, 35 comparisons of clinical, let's say, interest. In the ones that are marked in yellow, we have, as a laboratory, have participated. And the other also working groups, the inorganic analysis, has held 2 comparisons for, obviously, inorganics in blood, in clinical, specimens. And also the protein analysis has organized a few comparisons. So if you count them, you can find out that 16% of all the comparisons that have been organized worldwide for the past 20 years have been dedicated to support clinical measurements. And what do the metrology institutes get out of this is the documentation of their capabilities to support the measurements and connect them to the international system of units. I have used our laboratory as an example here. So if someone looks to find what Greece has, let's say, in clinical measurements, he can, let's say, just search for Greece and creatinine, and he can, or she can find out that we have a capability of measuring creatinine in serum in this range with expanded uncertainty of 2.5%. And this data can be used and provide evidence to work on the reference measurement procedures that are being used worldwide to support the calibrators that are in turn provided by the companies that provide the hospitals with the clinical analytical instrumentation to do the measurements in the real world, in the hospitals. If someone searches the internet for these capabilities, he will find out that he will get 372 results. Actually, of clinical relevance is 204, because the rest involve measurements in animal and plant tissues as well. And what do these measurements, let's say, support? We have the classic, let's say here, analytes and routine testing. We have some drugs. We have vitamin D. We have some drugs of abuse, steroids, and contaminants, PCBs, metals, of course, the electrolytes and essential elements, but also toxic elements, some uranium isotopes, and selenium methionine as a possible source of selenium. We saw again the same table regarding the comparisons of clinical instruments, and here in blue, you will see all the comparisons that have been performed till today, till this year, and concern the measurement of analytes in biological samples. The rest in white are measurements in solution calibrators or neat calibrants. What do these measurements have in common? They are all being done by mass spectrometry. So all the measurements that are in this, let's say, particular category are being done by mass spectrometry, and this highlights the importance of the technique in our life. So here is what we have at our laboratory for measuring and the measuring systems that we have in use. It is a high-resolution ICP mass spectrometer. You use it for measuring all the elements. A triple quad mass spectrometer, a QTOF MS, and an ion trap GCMS. These two are quite old, are going to be replaced this year, next year, with high-resolution spectrometers. Why do we need them? We need them because we want to support reference measurement procedures that supports also the measurement worldwide in clinical measurements performed every day in every hospital in all parts of the world. So this is the reason to have this system to support evidence for our health. We will show some examples from the comparisons that have been, let's say, performed till now. And classical one is cholesterol in serum. All the measurements that are provided by the institutes who have documented traceability, most of the institutes use materials that are in the key comparison database and are provided basically from the United States National Metrology Institute, NIST. The techniques in the particular study were GCI-DMS, ID stands for isotope dilution mass spectrometry, and LCI-DMS. The calibration that all the institutes were using were 1 point, others used bracketing, other 6 points calibration curves. And they validated their methods using a matrix CRM, in this particular occasion, NIST 909, which is a serum characterized for cholesterol. You see here the capabilities, that's to measure non-polar compounds in this particular area of concentration, metabolites in human serum. This is how the measurements compare. And because these campaigns have been performed also in 2000 and 2018, you can see how the metrology institutes are comparing. And you can see that the, let's say, results are within 2%. Moving to another case about creatinine, which is a particularly tricky metabolite to measure. You see here the same data regarding traceability, the techniques. Here, everybody is using LCI-DMS. Our laboratory data actually is here. We used on this particular measurement, LCI-DMS, we did 1 point calibration at exact matching, which means particularly we tried to measure, use as a calibrant, blood that had the same concentration as the unknown sample. Use several matrix CRMs, and the capabilities you got was this time to measure polar compounds in blood. This is how, again, the different the measurements compare between the institutes. And you see this comparability also in time. Iron in serum. This is quite a different measurement because this is done with ICP-MS. Again, isotope dilution is used. This time, the internal standard is is an isotope of iron. Like in the other comparisons, all the participants used labeled analogs of the measurand. Here you see again, this is the assigned value, and you see how the measurements compare. It's within, I think, 5%. And the last comparison that has been made, it was made piloted also by LGC. This refers to amino acids in plasma. It was particularly aimed at supporting newborn screening applications. The results of the participants, because this cannot be discussed and I have special permission for this, we cannot see who has participated, but you see that this is plus or minus 1 milligram per gram from all the institutes. These are the uncertainties. And because the previous talk was about vitamin D, I included a comparison with vitamin D that happened, I think, 10 years ago. Oh, sorry. This is how the Meteorology Institutes measure vitamin D, one of the metabolites. And you have an agreement between 1 nanogram per gram between the participants. We do also measurements with mass spectrometry to characterize the calibrants that are being used to calibrate the spectrometers, okay, because you need primary calibrants. This is an exercise regarding measuring amino acids in calibrants. This is phenylalanine, and you see here how everybody has measured the amino acid in a calibration solution, in an acidic aqueous solution, actually. All these measurements are being performed with IDMS with labeled phenylalanine. So, regarding mass spectrometry, also in clinical applications, but when we measure in meteorology, whatever, regardless of the substrate, is mostly done by isotope dilution mass spectrometry. So we need an internal standard. In the case of elements, we have stable isotopes, and we enrich the sample with a stable isotope. In the case of, let's say, organic analytes, we use a labeled analyte. In the case of creatinine, a deuterated creatinine was used. So we measure these ratios, the isotope ratios of the analyte and the internal standard, and we use this as a signal and not the particular signals of the compounds. This gives us the advantage that we reduce hopefully to zero the matrix effects that the sample might have, and at the same time also provide a very, let's say, realistic correction about the recovery of the measurements, because the labeled analytes are supposed to have the same extraction efficiencies like the measured compounds. If we do also this at 1 point calibration in, let's say, exact matching concentrations, then we have the best approach to the truth concentration of the unknown sample. We also need, if we want to have a, let's say, a reference procedure, we have to have a model that we know to know how our system, measuring system behaves. All of these IDMS techniques are represented by this model. This model works for biological compounds. This model is the same also for food, for environmental samples, for everything. It looks mathematically intimidating, but it isn't. And here we have also an uncertainty budget that has to be the end of any validation that we perform in our measurements. And this also gives us the opportunity to see what is the biggest, let's say, contributor to our measurement, to the measurement uncertainty, what we have to get better in order to get less uncertainty next time. So this refers only to the primary reference measurements in the traceability chain that I hope that everybody is, let's say, familiar with. And we start from the SI unit and we move to the patient result when you get a test from the hospital. What about the reference procedures? I described just with the previous examples that they have to be thoroughly validated. Okay, the validation procedure is straightforward. We have to account selectivity, specificity, the trueness, detection, the quantification capability, ruggedness, the robustness of the procedure. We have to have traceable calibration. We need to know the measurement model and also to have an uncertainty budget. But also we need this for the primary calibrated stores. This is also where mass spectrometry plays an important role. I'm going to move forward. We are going to just see the small, let's say, organic molecules, because the proteins and the peptides belong to another group. Valine was one of the test materials. And here you see mass spectrometry that reveal impurities in valine calibrators, other amino acids. This is done by mass spectrometry. Here are also the equivalents between the measurement institutes regarding the measurement of pure valine. Other drugs, for example, avermectin was the case of another comparison. Here we had a much more impure sample. You see the quantification is done by LC-UV, but the identification is done by mass spectrometry. And you see that several of the impurities have been quantified and identified, again by LC-MS-MS here. Once again, the results of the comparison. Regarding purity, there are some guidelines that have been issued, both for the absolute quantification of proteins and the traceability from the Protein Analysis Working Group regarding the SI traceable value assignment of pure compounds by the Organic Analysis Working Group. They are free in the literature. What else mass spectrometry can offer? It can offer the possibility to compare reference materials. Here we have a comparison where all the metrology institutes have provided creatinine CRMs and NIST, which has a JCTLM verified reference method, measured all these materials. You see that they agree within their uncertainties with a measured value, and they fall into a line with a slope of 1, which means that the assigned value was the one that was measured by the institute. So these calibrators are correct. So metrology institutes have provided materials that are, let's say, very useful. What else we can do? We can use mass spectrometry and reference values to evaluate other measurement processes. Here is, for creatinine, an example. This line is the reference line provided by the metrology institutes, and this is how other reference laboratories have measured. This is 20 years ago, a study by the IRMM, now the JRC, and you see for creatinine, the reference value here from the metrology institutes, and how hospitals measured. And this is a sample of 1,000 hospitals. Of course, unfortunately, we don't have data because these studies have stopped, but slowly they are getting started again. But obviously, accreditation and all the background that has been built till now has, let's say, ameliorated the situation. So the challenge is to get mass spectroscopy in a hospital for clinical applications, because this is what we are talking about, is difficult. Everybody has pointed out that we need first to validate laboratory-developed tests and put them into reference material procedures, a copious effort that is being done by the reference laboratories. And we again revisit this slide to remind us of what is needed to get a reference method. What are the pitfalls that we can get into? and this refers to the specificity, the trueness, the detection capacity, the quantitation. Actually, a couple of years ago, I had read a paper concerning vitamin D again, where some people were measuring a lubricant, pentaerythritol palmitate, that is isobaric, and were thinking that they were measuring vitamin D. So you can have various problems in your measurements. And are there actually RMPs available to support mass spectrometry in the clinical laboratory? If we visit the JCTLM site and click all the, let's say, opportunities we have, the choices we have for mass spectrometry, we get 152 results. Here are the molecules that are being supported currently. It's again the same, more or less, list with what we got from the capabilities. Again, steroids, vitamin D, some peptides and proteins, thyroxine, the regular, usual suspects here, some I think immunosuppressants. These are anti-epileptic drugs, and again, metals. This is also, let's say, underlining that the actual reality that mass spectrometry is used for basically for therapeutic drug monitoring, okay, and special applications currently. To move down to the chain, we have to solve several problems. Once, we have to have a need for traceable calibrators for all the materials that we want to measure, something that we are far from to succeed. We need universally applied protocols for the measurements we want to measure. Fast analytical response, this is something that is coming, is getting closer to reality with the new techniques in mass spectrometry, and need for specialized training, because mass spectrometry is quite demanding instrumentation. And because of all this, there are metrology networks that are being deployed in the European Union. One of these is in laboratory medicine. We think that through these networks, we can support actively these solutions. And particularly for traceability in laboratory medicine, you can contact Vincent Delatour or Gavin O'Connor, both members of the AFCC, get more information about how the EMN can help you in your problems with mass spectrometry. Thank you so much for your patience.
Thank you for your excellent talk. The presentation is open to questions.
Thank you, Ilya, for reintroduction into the metrology and the hidden world of this that most of us we have almost forgotten. But there are questions from the audience? Okay, go ahead.
Hello. I can hear you, yes.
Most of the reference methods that are based on isotope dilution do actually matrix. So you match the concentration of the analyte with the internal standard. So that's what you said, yeah? And
No, actually, no.
Okay.
This would be also very helpful because this reduces the uncertainty. It depends on who's doing the measurement and actually the procedures. It is different, let's say, approaches regarding who is validating the method. It's a choice of the analyst, let's say, or of the developer. What we are trying to do is to match the concentration of the sample with the calibrator. Actually, develop a calibrator that has the same concentration with the unknown sample. We do this, you do this, let's say, on a trial and error basis.
Okay, because I mean, I'm aware of some of those reference methods where you actually match the concentration of the internal standard. And I don't know if you're aware of those, but my question was just, are we doing, as a favor, doing this because we're introducing even more uncertainty in the reference method? I don't know if you can comment on this.
You are introducing more?
Variability, I mean, you're introducing more steps in your sample preparation.
Yes, by introducing, you mean the internal standard inside.
Yeah.
Well, the thing is that the isotope ratio is much more robust compared to the ionization problems that you might get, and you might not realize in the absence of a standard.
No, I'm not suggesting we should remove the internal standard. I'm suggesting you should have the same concentration across the entire range of the measurement, instead of matching the concentration. But maybe it will.
It depends on what makes the, let's say, the process more robust according to the, let's say, person that develops it.
Okay.
And he can judge from this, from the data he's getting or she is getting while he performs the validation.
Okay, thank you.
Thank you.
Other question? So, thank you again, Ilya and Chairman, for your presentations. And we continue on the next session with the sponsored satellites and WASP.